Alright, hello there. Today we'll be doing our 90th video. This is going to be our last graph problem until we get to advanced graph problems. It's graph valid trees. So in this problem we're using Leetcode. We're detecting if we're given n nodes labeled from 0 to n minus 1 and list of undirected edges to make sure that these nodes are connected in a way that's called a tree. A tree is one that has no cycles, and another thing is that all the nodes must be connected to all the other nodes. So one thing we need to detect is that we are going to try to detect if there are any circles, and the second thing we're going to try to do is detect if there are any nodes that are not connected. One way that I was thinking about doing this was that it was going to use a union find because we used union find earlier, and in redundant connections, we were able to detect if there were cycles. We detected if there was a cycle if they had pointed to the same parent, because if they started pointing to the same parent and we connect the items, that means that they are already connected and we're adding an extra connection, and that results in a cycle. Also, in the same time, if we're looking at the roots, there should be only one single root that all the items are connected by, because we're gonna pull everything into the one highest ranking item. So with that, we can definitely we should be able to use a union find to find the answer, to get the answer. Unfortunately, we are unable to do that. I did not look into it too deeply as to the reason why we're unable to perform this operation, but let's check it out. So of course, so roots is equal to well, it's gonna be if we do a dictionary, it's gonna be for node in n, and for each node we're gonna have a root item which is itself, pointing to itself. So that's the root, and the rank of the item is equal to let's say the same thing for node in n, and we want the rank to be 1 for every one item. Okay, with that, we have our root and our rank, and we need to create our find and union operators. So in the union, what happens in the union again is that we take two nodes, n1 and n2, and we try to get the roots of n1 and n2. So find root of n1 and find root of n2. So to do that, we need to find root operator, and we put a node in. And what is the root? The root is equal to n, while oh whoops, that's not a good variable because this is roots. So we need to let's just say r, while r root while r does not equal to the root of r, what we're gonna do is that we're gonna set the r equals the root of r. Also, the thing that was supposed to speed this thing up was to set the root of r. I mean, well, let's check it out again. Was this the, well, actually it's number of provinces here. It's to set the root of root to its root of its root. Yeah. Yeah, that's supposedly speeds it up. So anyways, then we actually return root. So we found the root, let's say, And now with the found roots, we're gonna check if root 1 equals root 2, then return false, because that means we have found a cycle based on the edges we see, and so we don't want to have those edges. Okay, and then we have this thing here. So otherwise, if rank of root 1 is greater than rank of root 2, then let's make the root of root 2 equal to the root to R1, and the rank of root 1 is now equal to plus equals the rank of R2. Else we have the opposite condition, and we just move all the items into R1 is equal to R2, and rank of R2 plus equals rank of R1. Let's just say greater than or equal to is fine. And we're going to return true, of course. So then we're going to do for a node in 4 edges for n1 and n2 in edges. What we're going to do is that we're going to union if not union node 1 and node 2. That means if we return false, they have the same parent, then we're going to return false because we found the cycle. Otherwise, we have processed all the edges, and we need to make sure that all the items, the length of the set of roots dot values are the same, because all of them should have the same parent. So then we should run the test. Range, right? Output data 1. Oh, equals 1. Haha, my bad. Great. That's how we do this problem. If it worked, but it does not. That gets 78% of the way there. So we do need to there. And then I looked up what Neetcode did in his way of doing it. I mean, theoretically it should work. I'm not exactly sure why it's not working. I believe it might. Let's print this length of the root values, and maybe it's there. Otherwise, we found a cycle but that doesn't make any sense. Let's submit it again, and we have, I think, 257 different root values, and that's really strange. They don't all have the same parents, so they're not connected in a way that's connecting all of them into a single tree, and that just means it should be false. But I might be missing something. Please inform me about what that might be. But other than this first option of relearning how to do a union find, which is great, we can do a we can do a thing called a DFS. We're gonna do what Neetcode has done, and with a DFS we can move traverse through starting at any particular node, wherever it is, however it's attached to its neighbors. We're gonna move through all the neighbors, and of course we're not gonna move back to our previous item. So we keep that in our DFS call, so that we know not to go to our parent item, but we keep pushing forward into all the neighbors, and to make sure that everything is visited. That means that we have everything under one tree, starting if we start one single node, if we do with DFS. Another thing is that we make sure that there's no cycle. That means that if the item is already in the visited items, then it's no longer any good. So first thing we need to do a DFS is to eliminate options here, this base case. So we need to make an adjacency list. Adjacency list. So adjacency list is to figure out like how our nodes are connected. So this is a node is connected to all these other nodes. So to make this adjacency list, so we do a for node n1 and n2 in edges. So and we connect these items in the list n1 dot append n2, and n2 is connected to n1. All right, great. So now we create a visited set, and we can now define our DFS call, where we have current and previous, and if the current item is already in the visited, return false. Otherwise, what we're going to do is set the visited dot add the current item, and for each neighbor in the adjacency list of the current item, we're going to run the check if that is the previous or not. If neighbor is equal to previous, we can continue. Otherwise, else, what we're gonna do is make sure. Well, yeah, that's cool. So what we're gonna do is for each neighbor, we're gonna run the DFS call. If not DFS of the neighbor and the current item as the previous, then we're going to return false. Otherwise, we're going to return true afterwards. And yeah, so with this, we're going to do a, what the heck are we going to do? I have no idea. We're going to run the DFS. Of the 0th item and -1. Run test. Submit. Wrong answer. Okay, so input data is an empty. Output is true. Right. We forgot. And n equals the length of visited. Run test. Send it in, and there we go. Pretty good submission. I think something that I need to do for these particular problems is that I need to write down exactly what I was thinking, because I kind of forgot that this particular piece of code. I need to really write down what I'm going to do and what the result should be, and before I start typing, because I forget by the time I get to the end. So yeah. Anyways, we don't need this else statement here. If we want to clean up this code a little bit, we can even do this. I guess. Yeah. Anyways. So that's the answer to this particular problem. What did we learn today? We learned to run the DFS call and to look at the previous items. That's very important. And to make sure we don't go to our previous items in undirected graphs. That is very, very important. That is another tool in our tool belt. How to build an adjacency list using the edges and the nodes that we have. So we were able to figure out if there was any cycles by checking for items in the visited, and we were able to check for the number of if all the items were in the tree by checking the length of the visited. And we also went through a union find and found out that it was not theoretically it was supposed to be possible, but then it didn't work out. For some odd reason, we ended up with 247 different ranks. That means we have not gone to the item, and well, anyways, with that, I think we have come to the conclusion of this particular video. I hope you enjoyed the video, and if you have any, please comment if you have any things to add, and I will see you in the next one. Thank you very much.